I'm going to be talking to you today about, I'm based in the UK these days, but was living and working in Australia, still working in Australia quite a lot, but now living in a slightly wetter country. I don't know, those of you that have seen the news, most of England is now apparently underwater. But the reference points I'll be drawing are from a much drier part of the world, where one of the major elements, I hesitate to say aluminium, in case you don't know what I mean, but if I say alumina, you might have a better idea, and the ore from which alumina is refined is bauxite. So it's bauxite mining, which is a form of strip mining that I'll be basing really what you can almost regard as a found experiment and some work we've done regarding carbon and microorganisms in soils after mining systems have been reconstructed. So the outline of my talk, I'm going to give a little context to climate change, and I think some of our plenary speakers later on today will be giving a lot more detail on that. Something about the forest, the biodiversity and restoration of these sites that may not be apparently obvious to people on this side of the world, and something about soil carbon development and the idea we've been working on of some vegetation feedbacks that may occur and the relationships between plants and soils and their feedbacks, which we think are important, and the missing link in that perhaps, which is soil microbial community development, which I'll be talking about primarily now in terms of carbon, in terms of carbon utilisation profiles, linking back into that carbon story. So we all know that atmospheric carbon is on the way up. It's risen considerably, and this figure just gives some ideas of some of the unpleasant things that might happen if we have a range of predictions here to take us to the end of the century, and all these unpleasant things that might happen. Some things very likely to happen, high probability, which might include things like the melting of the Greenland ice sheet, Arctic ice sea melt. According to these data that the predictions made are almost certainly going to happen, ending up with some pretty unpleasant endpoints for this situation if climate change continues to rise unabated. So a little bit about soil carbon and climate in particular. So we all know here in this room, I suspect, the importance of soil carbon. It's important on a global level, and from a carbon cycling perspective, it's quantitatively the most significant carbon pool at the Earth's surface. And as you can see from these data, the soil organic matter component of carbon gives us a very high proportion of the carbon at the Earth's surface held in other parts of the planet. It's linked to atmospheric carbon, and going to the theme of the conference, it has an effect on climate change. And carbon is stored, as we know, across the world in very different concentrations. In some desert areas it's very, very low concentrations, and of course in some peaty soils it can be at extraordinarily high concentrations. But if we want to sequester carbon or use soils to manage carbon, CO2 in the atmosphere, and pull that CO2 out, well, calculations have been made that increasing global carbon pool by just 5% can increase the amount of atmospheric carbon by 16%. So the opportunity is there, in principle at least, to make a great and wonderful difference if we manage our soils properly. And from when I was in Australia, very low carbon in the soils there, the chances of increasing carbon in the soils is quite good. However, there's a proviso. Whenever man has moved into an area and started using those soils for his own benefit, all we've managed to do is lose carbon. So we can turn that statement on its head. Okay, a decrease in the carbon pool of a further 5% can lead to an increase in the amount of atmospheric carbon by 16%. So we need to be aware of the risks as well as the benefits. Recently we've been doing some work in Western Australia and most of the data I'm going to show you is highly superficial, surface soils for various reasons. But we've also been looking at soils to depth. This is not true in recently glaciated areas such as the UK or Canada, but in ancient soils where the regolith can be extremely deep and roots of plants, of trees in particular, are known to exceed 40 metres commonly. We have soils that are incredibly deep. And we found carbon, which just published this work last year in Plant and Soil. So there's carbon at depths, at low concentrations, but consistently and persistently so at depths, 2 to 5 times greater than would be reported at a sampling depth of 0.5 metres. That is to say, if you look at the IPCC data on many of these areas, they would measure to 30 centimetres, 0.3 of a metre. What we found, taking a much more generous depth of half a metre and looking at what's under there, we can double or more the amount of soil carbon in these highly weathered landscapes typical of many areas in the southern hemisphere and in tropical parts of the world in particular. Can we change the amount of carbon in soil through land management? Well, a meta-analysis conducted by Roger Gifford some years ago now, 12 years ago now, has given us some indication, and there's further analysis. I think we might be hearing about some of that later on this morning. But the indication, the message I want to take from this is yes, we can increase or decrease the amount of carbon stored in the soil. There's no proviso on what sort of carbon that is, and I'll come back to that, but we can increase or decrease it quite substantially by land use change. How permanent that carbon is not clear. And we can't keep going forever. We can't keep putting more and more carbon in. There seems to be an idea that there is a saturation point, a saturation level, at which point you can no longer increase carbon in a particular system under a particular land use. As soil scientists, and many of us when we were growing up as soil scientists many years ago, talked about soil organic matter, which we know is slightly different to soil carbon, but it's sort of somewhat used synonymously now. And we need to bear in mind that the carbon we're talking about is primarily in organic matter, and it has a range of very important biological, physical and chemical functions, apart from anything to do with climate change. And as a general rule, more carbon is a good thing for all the reasons on this slide that I'm not proposing to go over now. I'm going to talk a little bit now about the forests I'm going to show you some data from, and biodiversity and restoration, and how they interact in these systems. The work, as I mentioned earlier, the work I'm talking about is based in bauxite mines, and these bauxite mines exist in 2 or 3 locations in Western Australia. They're very large mines, approximately 500 hectares are strip mined every year. The main one I'm going to be dealing with is the Eucalyptus marginata forest, the Jarrah forest, which is that little strip, not so little, that's probably all the woodland in England accounted for in that little strip, probably more actually, which is a unique, highly biodiverse forest system about which there has been some reasonably amount of good science done. And another forest which is Darwin stringybark, Eucalyptus tetradonta. And this is a large open savanna woodland cum forest system that dominates a lot of the northern part of Australia. It's poorly described. We don't know that much about the system. It covers an area similar to northern Europe pretty much. So it's quite an interesting opportunity to find out a little bit about this forest system. They are quite different, I think, to the boreal forests we have around here. Not only are these tropical forests, the northern one I will often refer to as tropical, and the southern forest is a Mediterranean type system, so they're tropical and Mediterranean systems. They're also highly biodiverse and floristically rich. The southwest corner of the world, where the Jarrah forest exists, is one of the world's 25 plant biodiversity hotspots. So it's a really important botanical site. I mentioned ancient soils. Well, the greenstone on Mount Saddleback, which is really a big hill that we've been working on, is over 2.6 billion years old. A little older than some of the soils around here, I'll warrant. And over 450 species of plants have been recorded at this one site, Boddington Mine, the Mediterranean forest site. That's about the third the flora of the UK on one hill. So that, just to give you an indication of biodiversity, it challenges Amazonia for biodiversity. There's animals as well, of course. When on field work, you're happier to meet some of these than others. But there are a range of unique, often endemic fauna as well. Now, I'm just going to give you an idea of how the mining progresses at these sites, so and what the profiles look like. So we have some idea of the starting point for the reclamation. In Australia, we would say rehabilitation, but really what this tries to be is restoration ecology or ecosystem reconstruction. That's the sort of general underlying principles of what the mining companies here are trying to achieve. Okay, so we have this environment which is then stripped of all its vegetation, the wood is sold off, and a load of the scrubby vegetation is retained. Come back to that later. Then various soil layers are taken off, the topsoil, the subsoil, and the gravelly material, that are piezolytic gravels, are also removed, which just leaves a layer of lateritic caprock. That can't be dug, so it's drilled and blasted. And that material from there on is just a dig and load operation, very simple dig and load operation. And where the sites are hilly, you develop some sort of pits. Other sites are flat, and it's just a lowered landscape, basically. At that point, there's a decision made the ore is all gone, and the site is prepared for reclamation, restoration. First thing that's happened is that it will be deep ripped or subsoil. The mine floor will be loosened in some way to allow root development, and we mentioned how deep the roots go in these systems. It's often landscaped a little bit, and then in reverse the materials are put back on, so we have the topsoil at the top and so on. Then this scrubby stuff was taken off, was put back on to create habitat piles to allow easier recolonisation of fauna. Now, what I've shown you happen there doesn't actually happen in that way. What they want to happen, and doesn't always happen, is that it's direct returned. Are we all familiar with that term, direct returned? Some are, some aren't. So direct returns means as the material, the topsoil comes off and the subsoil, it's taken straight to another already mined out site and put back on the same day. In this way we can retain the maximum integrity of the soil and biological activity. It is not perfect, it is not damaging an ecosystem, it is still destroying it, but it's better than stockpiling it for 5 years in a big heap. So and then planting occurs, there's seeding, there's outplanting, there's even tissue culture banks that for more recalcitrant species that cannot be grown from seed. Over 100 species are typically sown at these sites, to give you an indication of the biodiversity they're trying to put back. And then we can go and look at those sites. We get a sort of pseudo-chrono sequence that we can go and look at. I'm sure you're familiar with this sort of system from these parts of the world with the various mining operations that take place around here. So that's giving you some indication of the starting point. So now we're going to look at carbon development of vegetation feedback in these systems. And how we've done that is by using a pseudo-chronosequence. So everyone uses the word chronosequence. It really is a space for time substitution experiment or observation of a found experiment, because we can go to a number of these sites and visit them all on a day if we wish and we're quick. But we haven't visited them at different times. Now, I live about 4 miles from Rothamsted Experimental Station. And many of you here will be familiar with the classical experiments at Rothamsted, I'll warrant. There they've been monitoring the soils and taking soil samples for over 175 years now from Broadbalk and slightly less from some of the other experimental fields. And there you can go to the soil store and visit the soils, and you have a chronosequence, a true chronosequence, because they were taken, the crops, the plant material, the soils taken through time. This is a pseudo-chronosequence. It's a time series based on space for time substitution. And we should always be aware that we have these differences in spatial sampling as well as temporal age of the system as we make these observations. But generally speaking, you can get some sort of feeling for systems that work. Here's some basic data on basal area of trees. The green sites on closest to me here are lots of native unmined forest sites, and there's a general trend through various restored sites leading up to about 26 years there. But we're interested in what's happening at the feet of the trees, and the first thing we often look at is the litters and how the litters develop in these systems. So here, surface litter development from the 2 sites, the Eucalyptus tetradonta site at Gove, which is the tropical forest, and the Mediterranean site, the Jarrah forest, down in southwestern Australia. And in both cases we can see through time we get a litter development that overshoots the amount of litters that fall in native systems. And this is quite common in redeveloping forest systems. It's an observation that's been made before. It's expected partly because of stem density, partly because we're putting back a natural forest all at one go, and there's successional processes that come into play. But it's also a risk because there's a fire risk here. These are Australian systems that burn, and that needs to be managed as well. And there's also a great deal of extra biomass produced because these sites have been heavily fertilised. They've been fertilised pretty much at agronomic rates, even though they are pea-sensitive ecosystems. Many plant species within this forest system are very poorly affected and can show even toxicity symptoms when subject to elevated levels of phosphorus. So we can look at the litter in a bit more detail. We can try and identify the different types of litter by their morphology, whether they're comminuted or they come from the key eucalyptus plants there. And we also can measure the amount of woody debris. We can see in this one here that we have a considerable amount of woody debris building up, and that woody debris there is related directly to the successional processes, because by about somewhere between 1999 and 1996, in terms of the time frame of these forests, many of the acacias would naturally senesce and die. And hence we get this big influx of wood, of small woody debris and a lot of woody litter on the sites, which some fire ecologists just refer to as fuel. So there are some issues in managing these processes. Another interesting issue, though, is how does the development of the flora, and does indeed the development of the flora, lead to carbon quality developing in those soils? Do we see differences in carbon in relation to this? Well, if we look here, I showed you some data from 40 metres down. Here we've gone the other extreme. We've looked at the first 10 centimetres of soil over a 26-year chronosequence in very close detail to try and understand how developing system is affecting carbon in the soils. And as you can see, over a number of years, it overshoots considerably, and that's probably related to the amount of extra litter that's falling onto the soils, the extra litter supplied both leaf litter we see from above, and no doubt some root necromass contributing towards that. There's a line I put in here which sort of represents the average amount of carbon found in the top 10 centimetres of soil in native forest sites in the area. So we visited several others and did a data search as well of other data sets, and that's about where it comes in at. So much of the carbon in the surface soils here, very, very much higher. And from a superficial carbon sequestration perspective, that might sound great, but there may be other implications to this that come down the track. Also, we notice as we go through time, we seem to reach a point where it doesn't accumulate anymore. However much more carbon we're putting in, with the litter still falling, there's no further increase in carbon, even in the top centimetre of mineral soil in contact with the litter layer, which brings us back to this model I showed earlier. Seems to suggest there may be some validity to it. So now I'm showing you an image here of the site at Gove in the tropics. This is a picture of a site that has been just had direct return applied to it. Direct return soil, topsoil lying on it there, and that is last year's mine site. And you can see by the trees way off in the distance, get some indication of the scale, and they would be doing 2 or 3 of these. They call them pits, but they're not pits, they're just large areas of flat land. Occasionally there's ore quality isn't good enough, and there's islands isolated in the landscape. You suddenly see an island of a few hundred hectares where they've decided not to mine, and that sits about 6-8 metres proud in the landscape. Quarter of a century later, it kind of looks a bit like a woodland or a forest, and generally the floristic indicators indicate success. But if we look at percentage carbon in this tropical site, this is different to the different site to the one I was showing you a moment ago at the Mediterranean system. We also overshoot. This is model data in this case, and what we notice here, and I'll be coming back to this carbon story with the microbial biomass later. What we see here is the microbial biomass only ever reaches about 2/3 of where it was in the original forest systems before they were disturbed. So this suggests to us that there's some sort of biological dysfunction. Now, when you look at the litter loads being close to twice as high, and in fact when you walk on some of these forests, like that very picture there, it's like walking over a mattress. The depth of the litter not so different to the depth of this stage. Something's going wrong. More carbon being sequestered, but we don't want litter layers that are like mattresses.